Okay, so hi everyone. In this video, we are going to discuss about bipartite na graphs. A simple graph G is bipartite if the set of all vertices V can be partitioned into two disjoint subsets V sub 1 and V sub 2, such that every edge connects a vertex in V sub 1 and a vertex in V sub 2. In other words, there are no edges which connect two vertices in the same subset or in the same partition V sub 1 or in V sub 2. Okay, so let's have this example. So the set of all vertices V is composed of all these nodes or vertices in this graph. So that will be A, B, C, D, E, and F. However, we said that if a graph is bipartite, it is partitioned into two subsets, V sub 1 and V sub 2. In this case, our set V sub 1 is colored red and it has elements A, B, C, and D. And the V sub 2, partition V sub 2 on the other hand, is composed of E, F, and G, which is colored in blue. And then we also said that every edge connects a vertex in V sub 1 and a vertex in V sub 2. If we check each of the edges here, we see that these are connecting vertices that are part of V sub 1 and V sub 2, but not of vertices that belong to the same na partition. Okay, so we said here that there are no edges which connect two vertices in V sub 1 or in V sub 2. Okay, and if we check this edge, it connects A, which is from V sub 1, and F, which is in V sub 2. This edge, on the other hand, connects B, which is in V sub 1, and E, which is in V sub 2. And the same is true for other na edges. Okay? There are no such edge that connects two vertices belonging in the same partition or the same subset. Okay? So this is also an example of a bipartite graph. So we can see that there are no edges that connects vertices that belong to V sub 1 or no vertices that are connecting vertices between vertices in V sub 2, and all of the edges are connecting vertices that are belonging in V sub 1 and V sub 2. Okay, and this one is also a bipartite na graph. All of the elements in V sub 1 is connected to an element or a vertices in V sub 2. Okay, so if this is a bipartite na graph, then this, on the other hand, is not a bipartite na graph. So this violates what we said, that the graph of G must be partitioned into two disjoint subsets. But in this case, since B and C and D are connected, so they are not disjoint. This V sub 1 is not disjoint. Okay? Now, let's have an example. Which of the graphs are bipartite? So let us start with this graph. But before that, let us define what our technique would be. So one way to do this, or one way to determine if a graph is bipartite, is by coloring the graph. So we are going to use two colors. So we are basically coloring the vertices using two colors in such a way that vertices of the same color are never adjacent along an edge. Okay, so let's have an example to make it more understandable. So we are going to use two colors, red and blue. And you can start with coloring with any vertex. So in this case, I am going to start with A. And since I started with A and colored it red, then adjacent vertices to A must not be red. So in this case, the B, the H, and the C must be colored blue. Okay, now let's start with, assuming that I started from H. The adjacent vertices of H must not be blue. Okay, so we color E and F to be red. And if we check the if this edge violates the rule of the bipartite, we can see that it does not, since they are of different na color. Now, the adjacent na vertices of F and E must not be red. So F is connected to H, C, and G. So we must color G as blue. Okay, on the other hand, the E must not also, the adjacent vertices of E must not be red as well, which is B, H, and G. So it is correct. And the adjacent vertices of B, G, and C must not be blue. So we are coloring D as red. And if we check the adjacent vertices to D, which is B, G, and C, they are also not red. So there are no adjacent sides that are of the same color. So we can then say that this graph is bipartite. And we can also verify it by restructuring our graph into this, into two disjoint subsets. So all the red nodes are A, E, F, and D. And all the blue nodes are B, H, G, and C. As you can see, we have retained here the edges and the connections which are from this graph. So A is still connected to B, H, as well as C. And E is still connected to B, H, as well as G, and so on and so forth. You can verify it yourself. Okay. So let's go to the next example. And we also have this graph. Is it bipartite or not? So let us color this graph into red and blue again. So in this case, I just started with G. Okay. And the adjacent vertices of G must not be red. So we colored it blue. And there are no adjacent sides that are of the same color. So every other vertex that are connected to G is color na blue, and no vertices of color blue are also connected. So we can say that G is, this graph is a bipartite na graph. Okay, and we can also restructure our graph into this form. So we separate all the blue and the red on the left and the right side, and we retain the connection. Okay. Now, let's have more complicated examples. So this is from the Rosen textbook. You can check it out. So we have a graph H as well as a graph G. So which ones of these graphs are bipartite? Are both of them bipartite or not? So the only difference here is that in graph H, there is no connection between B and D. But for graph G, there is a connection between B and D. Okay, so let us begin with this one. So I started with A. So I colored the node or vertex A with the red. So the adjacent vertices of A must not be red. So the adjacent vertices are G, E, as well as C. So we colored it blue. Now, the adjacent vertices of G, C, and E must not be blue also. So in this case, I just started with E. So E is adjacent to A, B, and D. So we colored it red. And if we check here, B, the connection of B is connected to C, E, and F, which is not yet colored. Okay. Now, so we must ensure that the adjacent vertex of B is also not red. So we color F as blue. So if we check the adjacent vertices of F, so it is A, B, and D. And we can see that they are all of the same color from F. So no adjacent sides are of the same color. So we can then say that this graph is bipartite. Okay, so let's have another example here. So in this case, there is a connection between B and D here. So I also started with A, and let's color its adjacent vertices. So that will be G, E, and C. And we colored B and D, which is a neighbor of C. So since all of the adjacent vertices of C must not be blue, so we color this red. However, the adjacent sides B and D are of the same color. So they should be B and D. Okay? And so we can say that they are not bipartite. Okay? So yeah. So this is the difference between graph H and the graph G. So it is only graph G that is bipartite, but not graph G. Okay, now let's move on to complete bipartite graphs. So when we say complete graph, so just a quick review from the previous topics. And if you want to know more about complete graph, you can watch my video, separate na video on this. So a complete na graph on n vertices, denoted by k sub n, is the simple graph that contains exactly one edge between each pair of distinct na vertices. But when we say bipartite na graph, so what we mean by complete graph is that every vertex is connected to every other na vertices. Okay, but a simple graph G is bipartite on the other hand, if we can partition the set of vertices into two disjoint subsets V sub 1 and V sub 2, and there are no edge that connects vertices belonging in the same subset. Okay, so what if we want a complete bipartite graph? So what can we do with that? So this is an example of a complete bipartite na graph. So in this case, all these vertices A, E, F, and D are not connected at all. Okay, the same with the vertices belonging in B, H, and G. They should not be connected, and the edges that we should have should only be edges that connects a node from this set to this set. Okay, so in this case, A is connected to B, H, and G. All of the elements of this subset, blue subset. E is connected to all of the other subsets also of, let's say, V sub 2 of the blue subset. F is connected to all of the elements of the blue subset or nodes of the blue subset. And D is also connected to all of the elements of the blue subset. So in this case, we can say that it is a complete bipartite na graph. Okay, so these red and the blue subset are totally disjoint sets, and every other vertex in red subset is connected with every other na vertices in the other na subset. Okay, so this one is a bipartite graph but not complete. Why? A is connected to H and G but not to B. E is only connected to B but not to H and G. F is only connected to B and G but not to H. And then D is connected to B but not to H and G. So we can say that this is a bipartite na graph since they are of disjoint sets and the edges are connecting vertices from the two partitions or two subsets, but they are not complete. Okay, and this on the other hand is, sorry, let me just redo this part. This on the other hand is not a bipartite proof because if we check this, there is a connection between F and D wherein these two nodes are belonging in the same subset. Okay, now this is actually the formal na definition na. So a complete na bipartite graph, K sub M and N. So that means that M refers to the number of vertices in V sub 1 and N refers to the size of V sub 2. that has its vertex set partitioned into two subsets V sub 1 and V sub 2, such that there is an edge from every vertex in V sub 1 to every vertex in V sub 2. Okay, so this is already the formal definition of complete bipartite net maps. So in other words, we have here partitioned V sub 1 and then V sub 2. So V sub 1 has only 2 na vertices and 3 na vertices on the other hand for V sub 2. So K of 2 and 3 is a complete na bipartite graph. So as we can see, all the nodes in V sub 1 are connected to every other node in V sub 2. And the same as true for this example. V sub 1 having 2 elements and V sub 2 having 4 elements. And all the elements in V sub 2 are connected in every other element of V sub 4. And same is true for the rest of the examples. Okay.